Alright, I'm gonna get started in my next video. So we're gonna talk more about biking, miles per hour. Last time I had a list of distances that I biked. It was 29.41, 30.63. These are all in miles. Use miles. Let's see, 21.25 miles. 25.88. 30 and 30. So some of these are new additions. Can't remember which ones on this list were the same numbers as last time, but one thing that I wanted to do differently in this video was take into account the amount of time it took to go these distances. So it may look like there's a lot of variety here, some exactly the same, but some a lot different, and that's because of the amount of time spent biking. So for example, I biked 29.41 miles in 80 minutes. I biked 30.63 in 80.5 minutes. I biked 21.25 miles in 56.5 minutes. I biked 25.88 miles in 72 minutes. And I biked 30 miles in 80 minutes. And on a different day, I also biked 30 miles, and it took 79 minutes. So the first thing I want to do is kind of take these numbers and put them into miles per hour. So as you can see, sometimes I spent more than an hour. Most of the time I spent more than an hour. One time I spent less than an hour. But so I want to do something that kind of normalizes these numbers and turns them just into miles per hour. So what I started to do was to write, for example, 29.41 miles. I set it equal to 80 minutes. That way what I'm saying is if I've gone 29.41 miles, I've biked for 80 minutes. If that's the case, then I can divide both sides by 80 minutes, and on the right side I just get 1, so I get 29.41 miles over 80 minutes, and that gives me a unitless number of 1. But really so really what I want is so this will give me miles per 80 minutes, which is not exactly what I want. What I really want is miles per hour. So if I write this again, 29.41 miles is equal to 80 minutes. What I want to do is I want some X miles in terms of 60 minutes, because there's 60 minutes in an hour. So the way that you approach this is, if I'm trying to find this value in miles, I take this number divided by this number and then multiply by this number to get back to x. So that's kind of what I started doing is so 29.41 divided by 80 minutes and then times 60 minutes gives you 22.06 miles per hour. So that's the first day. If I did 29.41 miles in 80 minutes, then I would do on average 22.06 miles in 1 hour. So I'm gonna do the same thing with the rest of the values and get the corresponding miles per hour. So this one I said was 22.06 miles per hour. This one, if I divide 30.63 by 80.5 and then multiply by 60, you get 22.83 miles per hour. And same thing, if I take 21.25 divided by 56.5 and then multiply by 60, you get 22.57 miles per hour. 25.88 divided by 72 times 60, let's see, gives me 21.57 miles per hour. And on this date, when I did 30, so you take 30 divided by 80 times 60, and you get 22.50 miles per hour. And finally, 30 divided by 79 times 60 gives you 22.78 miles per hour. So see, even though on both of these days I did 30 miles, the miles per hour number is different. So there's no, in my last video I had I had a bunch of equations, and some of them were similar numbers, and I had to do some kind of do a couple tricks to get unique values out of them. But in this case, they're all different numbers, so that's going to be a lot more easier to calculate. So last time I talked about the number of points needed to define a certain curve. If I have just a line, all I need are 2 points in order to know the equation for the line. If I know a starting point or a midpoint and an end point, I can describe the entire line. And a line has the equation in the form y equals mx plus b, where y and x are variables and m and b are constants. They're just not known. So we just put a dummy letter in its place until we solve for it. For a parabola, you need at least 3 different points to describe it. So if you have a parabola that kind of has this shape to it, and this is y equals, I'll say, ax squared plus bx plus c, where again y and x are variables. They vary. Like we could stick any number into x to find out what the corresponding y value is. However, a, b, and c are fixed values. They don't vary. They're constants. We just don't know what they are, so we just put a letter in place as a placeholder. So the pattern continues. If you had some sort of curve that was maybe of the form y equals ax cubed plus bx squared plus cx plus d, this equation, you would need 4 points in order to be able to describe this curve, and so on and so forth. So that being said, we have a whole bunch of points. We have 1, 2, 3, 4, 5, 6 points. So assuming some kind of random spread of points, 1, 2, 3, 4, 5, maybe 6, there is an equation that where the curve will pass through all of these points. Now it may look like this. It may look like this. There's, well, not at the very end, but let's see. I keep missing that last point. It could look like that. It could have any kind of shape, but the point is there's at least one equation that draws a curve through each one of these points, and what I'm going to do is I'm going to solve for that equation. So following this premise, we have let's see, we have 6 points, so the equation is going to have the form y equals a x to the 5th plus b x to the 4th plus c x to the 3rd plus dx squared plus gx plus h. So the way that I'm going to solve this is to again make a list. I'm going to make a list of all of the well, let me just write it out. So putting in place these values, we have 22.06 for the y value is equal to a times what? So in this case, each of these represents an incremental day. So this is day 1, this is day 2, this is day 3, 4, 5, and 6. So on day 1, x represents the day. So plus b times 1 to the 4th plus c 1 to the 3rd plus d 1 squared plus g times 1 plus h. So that's the first equation. The second equation goes 22.83 is equal to a. Now we're on to the second day, plus b 2 to the 4th plus c 2 to the third plus d 2 squared plus g times 2 plus h. The third day, we have 22.57, and it's the third day, so x equals 3. And we have 3 to the fourth. Then we have 3 cubed. Then we have 3 squared. And 3 plus h. For the fourth day, let's see, 1, 2, 3, 4. The fourth day is 21.57. It's equal to a. Now it's the fourth day, so x equals 4 plus b 4 to the fourth plus c 4 cubed plus d 4 squared plus g times 4 plus h. Okay, so it's 1, 2, 3, 4, 1, 2, 3, 4. So now we have 22.50. It's a 5 to the fifth plus b 5 to the fourth plus c 5 to the third, plus d 5 squared plus g times 5, and then can I fit a plus h? And for the very last one, 22.78 miles per hour, and that occurred on the 6th day, plus b 6 to the fourth plus c 6 to the third plus d 6 squared plus g times 6 plus h. See, the h just comes along for the ride. Okay, so now that I have all 6 of my equations providing me 6 unknowns, all these constant a, b, c, d, g, and h are unknown, but I have 6 equations with 6 unknowns. That means I can solve this for each of the unknowns. And the way that I want to do that is I want to make a list of all of the coefficients of the unknown values. So I'll start with the first equation up here. I have 1 as the coefficient to a, and 1 is the coefficient of b, 1 is the coefficient of c, d, g, and h. And the coefficients in the second column, or second row, sorry, is, let's see, 2 to the fifth, which is 32. 2 to the fourth is 16. 2 to the third is 8. 4, 2, and 1 for h. Next on the next row is the 3's. So we have 3 to the fifth, which is 243. 3 to the fourth is 81. 3 to the third is 27. And then we have 9, 3, and 1. So on the and then on the fourth row, let's see, 1, 2, 3, 4. So I'm done with that one. Done with that one. Done with that one. Now we're on to the fourth row, where we have h is 1. H is going to be 1 for each of them. And we have 4, 16, this is 64, this is 256, and this is 1024. And then we have h is 1 again, and we have 5, 25, then we have 125, and 625, and 3125. And for the final row, we have 1, 6, 36, 216, 1296, and 7776. Okay, so that is a list of all the coefficients to the unknown constants. And we are going to multiply that by a list of all the unknown constants, A, B, C, D, G, H. And we are going to set those equal to a list of the solutions, which are, let's see, 22.06, 22.83, 22.57, 21.57, 22.5, and 22.78. Okay, so these three lists encapsulate the 6 different equations and 6 unknowns. So the interesting thing about having the 6 equations like this in this form is that you can still manipulate them in the same way you could when they were individually written out. Like, if I wanted to multiply this whole row by 3, I can do that. I would just multiply by 3 here, multiply by 3 here, multiply by 3 here, multiply by 3 here, so on and so forth. And I could do that. I could do that to any of these rows. Like if I multiply the first row by 3, all these would be 3s. And then I would have to multiply this by 3 as well. But so what I want to do is kind of use different tricks to again, this is a matrix. This is a matrix. And this is a matrix. What I want to do is I want to get this matrix into a form called it's called an upper triangular matrix. Let's put a triangular. And an upper triangular matrix has the form where all the diagonals in the list are 1, everything below is a 0, and everything filled in below is 0 for all these. These numbers can, anything above can be whatever, but my main goal is to get all 1s in the diagonal and all 0s below that. So the first the first thing I'm going to do is I'm going to get a 1 in all these diagonals. And the way that I'm going to do that is, for example, for this row, for this entire row, I'm going to divide everything by 16. So if I divide everything by 16 in the second row, let me move this down a little bit. So again, the first row will stay the same. There's 6 ones. And then in the second row, I'm going to divide by 16. So 32 divided by 16 gives me 2. 16 divided by 16 gives me 1. 8 divided by 16 is 1/2. And 4 divided by 16 is 1/4. 2 divided by 16 is 1/8. And 1 divided by 16 is just 1 divided by 16. And then not forgetting that the solutions also change. They have to be, so the first solution stays the same, 22.06, but the second solution, since I divided everything on the left side by 16, I also have to divide everything on the right side by 16, and you end up with 1.427, let's say. It goes on, but it's pretty close to that. So that takes care of the first row so far and the second row. So for the third row, I want to get a 1 in this position, so I'm going to divide everything by 27. And with that, that's going to equal, if I just go down the line, 9, 3, 1, 1/3, 1/9, and 1/27, and you end up with a number that looks like 0.835, let's say 836, and it goes on. So that takes care of this row. The next one I want to get is a 1 right where the 16 is, so I'm going to divide everything by 16. 1024 divided by 16 is 64. 256 divided by 16 is 16. Then you have 4. Then you have 1. Then you have 1/4. And then you have, what is it? 1. Hold on. Alright, so I just went through and divided each row out by the diagonal unit. So I got all 1s in the diagonal. For this row, I just divided everything by 4. This row, I divided everything by 5. In this row, I left the same as it was from the beginning. So the next step gets a little bit tricky. So probably what I'll do is switch over to Excel just so I can do this a little bit cleaner. Alright, so I moved all the values over into a spreadsheet because I think it'll be a little bit easier to manipulate everything. What I'm going to do is I'm going to keep the first row as it is, just going all the way across, and for the second row I'm going to do something interesting. I'm going to say that this row is going to equal this 2 times the top row minus the second row. And you'll see why that's helpful. So if I just say 2 times the first row minus the second row and hit enter, that puts a 0 in this first place, and I drag that over so that all the other cells do exactly the same thing. So what I'm doing, whatever I'm doing to one side, as convoluted as it is, I can do it as long as I do it equally distributed across the entire row. So what I'm going to do, and that does exactly what I want. I want to keep a 1 in the diagonal, and everywhere below the 1 I want a 0. So for the third row, I want to set it as equal to 9 times the first row minus the third row. But we run into an issue here because as I drag this over, I want a 0 here still. I want a 0 here and I want a 1 here. So what I actually have to do is add a subtract, and that value is a 6, so it's 6 times, and I'm going to set it equal to this row because that keeps the first value a 0 and it also removes the second value. And if I bring this all the way across, I'm almost there. I have a -1 there. I want a 1 there. So all I have to do is set the whole thing equal to the negative value of it. And I actually want to do that for the whole row. So I'm going to just drag this all the way across. So far so good. We got 1s in the diagonal and we got 0s everywhere below. Continuing on to the fourth row, I want to set it equal to 64 times the first row minus the fourth row. And that puts a 0 there just like we want. If I drag this over, now we have a plus 48. So I have to subtract 48 times this first row. And then I drag that over, that gets rid of the 0 here. Now I'm stuck with the minus 12 here, but that's easy. We just do plus 12 times, I want to do the third row. And as I drag that over, now we're left with almost 1. What I'll do is I'll just divide the whole thing by point, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see, did that do it? I want to do divide by. Yes, that did it. And now for the fifth row, I'm going to set it equal to 625 times the first row minus the fifth row. And we get something like 500. So I'm going to multiply 500 times this and subtract it. Hopefully I subtracted, yep. Now we're left with a minus 150, so I want to add 150 times the third row. I'm going to click and drag this over. So we need minus 20 times the fourth row. Ooh. Let's see. there's a little bit of a rounding error going on here. That's why we're seeing this. But it's a 1, 2, 3, 4, 5, 6, 7, 8, 9. I think. So I want to add 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? Let's see. Yep. And then if I just divide this whole thing by this number, by negative 1.123456789. Perfect. So now we have what's called an upper triangular matrix, because we have the first number in each row is a 1 and everything below that is a 0. And what that allows us to do is solve for each constant directly. So if I say B, C, D, G, and H, let's see, 1, 2, 3, 4, 5. I'm not done. I always do that. Okay, so for the last row, right? We need 7776 times the first row. Hold on. This is equal to 7776 times the first row minus the last row. And that gets us here. 6480 times this row. Plus 2160 times the third row. $359 7 times this row. Ugh. I don't know why I'm getting these weird rounding errors. But what ends up happening to this row, I'm just going to do this, and the last number is 29.98. So now I'm ready to solve directly. If A, B, C, D, G, and H. What this bottom column is telling me is, if I remember the way this is set up, is all these coefficients multiply against the unknowns and equal a solution. But what we have in this first row is we have 0 times A plus 0 times B plus 0 times C plus 0 times D plus 0 times G plus 1 times H equals 29.98. That means H is equal to 29.98. Similarly, G is just equal to the solution minus 2.2833331 times H. And D is equal to the solution of D minus this number times G minus this number times h. C is equal to ABC, the solution for C, minus this times this, minus this times this, minus this times this. B is equal to the solution of B minus this times this, minus this times this, minus this times this, minus this times this. And for A, one of each of the unknown constants is equal to this value. So that's just this minus this one minus this one minus this one minus this and this. And you get these are the solutions to the unknown constants. Okay, so I've brought up all the data points, all the miles per hour that I did on each day. So day 1, day 2, day 3, day 4, day 5, and day 6. So here's day 1, here's day 2, day 3, day 4, day 5, and day 6 is right there. So as you can see, we have our equation, which is ax to the 5th plus bx to the 4th, cx to the 3rd, so on and so forth. And for each of these constants, I just put in the values that I solved for using the list matrices. And as you can see, we do indeed have an equation that hits all of those points. But one of the main things I wanted to bring up in this video is that you see, unlike my last video where we had like a line showing a trend, in this case we have exact values, which may seem like a good idea. It may seem like you're gonna get like even more accuracy with your predictions about, you know, future biking. But as you can see, as I zoom out, the values just, they go off the map, and they actually go negative in some places and go up to infinity in other places. So it actually doesn't do you as much good to solve for an exact equation. It's better to solve for a trend and therefore gain, you know, insight and better predictive ability with like the future biking. I guess that's it.